present here. I welcome you all to the CIT Quantum Hackathon 2022 workshop series, sponsored by IBM Quantum as a part of this Fall Fest. With this, I'm extremely pleased to welcome our guest speaker, Ms. Sabyatha Gupta, PhD candidate at Institute of Theoretical Physics, LUH, Hanover, where she works on the physics of quantum many body systems. She completed her master's in quantum science and technology from the University of Barcelona. She is Swiss advocate and was previously a co-op at IBM Quantum. Ma'am, once again, I welcome and extend my sincere gratitude to you for taking the time to share your quantum knowledge and experience. We are so thrilled to listen to you on the topic and essay from grade 5 and quantum computing. The session is all now yours.
Thank you for the very kind introduction. Good morning, everyone. I am very pleased to be presenting here today. I'm certain that, firstly, I would like to check, am I sufficiently audible?
Yes, ma'am.
Okay. I'm certain that you have had a wonderful week of learning. I would today, I would like to talk about some of the quantum algorithms that are not generally talked about much because of there are many famous algorithms like VQE, QAOA. I would like to talk about the quantum algorithms that solve linear systems of equations. Before I begin with business, I would really like to talk about some recent events. As you may know, the Nobel Prize in Physics was recently announced, and this year's Nobel Prize was shared by three scientists, Elaine Aspect, John Clauser, and Anton Zeilinger. And the press release for the Nobel Prize Physics announcement reads as follows, that it was awarded for experiments with entangled photons, establishing the violation of Behn inequalities, and pioneering quantum information science. If you read further the press release, it says that the ineffable effects of quantum mechanics are starting to find applications. There is now a large field of research that includes quantum computers, quantum networks, and secure quantum encrypted communication. I think we can all take this moment to appreciate this announcement a bit more, and I believe that this might be the best time to begin with or keep learning more things about quantum sciences. I remember that when I was young, about in grade 5, we were told to write hopeful essays about technologies we would like to see in the future. For people in the audience, you might have also had an opportunity to write such essays about future technologies or what science can do in future for us. I would like to talk about that for a moment. In fact, it is one of the things which I enjoy most. If you can go on the following link and there's a very short question for you to answer, or you can follow this QR code. Meanwhile, I'll also drop the link in the chat and we'll take 30 seconds to give our answers and we'll analyze the answers. I would really love if all of you participate in this. I'll give it 20 seconds more, and then I'll share the answers that I have got in my previous sessions and in this session as well. Well, there are some very interesting answers here. I would like to pick the ones that possibly encompass all of these answers, which are related to computing. Computing has played an important role in development of all technology in the past 100 years. Now we'll go back to our slides. Let's talk a bit about evolution of computers in the past 70 years. Around 1947, John Bardeen, Walter Brattain, and William Shockley invented the first transistor at Bell Laboratories. Before that, the size of computers was as big as the room, but with evolution of the transistor, the size of the computers became more and more compact, and with further development in technology, faster and faster computers came into being. Around the 1970s, Intel introduced its first microprocessor, which could perform 60,000 operations per second and had about a memory of about 640 bytes. Then in 1999, a lot of things happened, but I was also born. It has nothing to do with evolution of computers, but I just wanted it to be there. And now in 2022, I think we are all aware that powerful computers already exist. The world's second most powerful computer has this many bits of storage, which is 1, 2, 3, 4, 5, 6, at least 8, 10 to the power 18 bits of storage. But compared to something as simple as we see in our daily lives, coffee, the molecule caffeine needs about 10 raised to power 48 bits of storage to be able to be simulated properly on a computer. Even though we have powerful computers right now, there is still room to address many problems that we cannot attend because of the computers that we have today. Which brings us to the importance of quantum computers. The concept of quantum computer has been around theoretically for over 3 decades. A quantum computer is a simple device that uses laws of quantum physics to represent and process data. They are claimed to show a quantum advantage, that is, exponential information storage, capacity, faster processing, and solutions to otherwise unsolved problems. The building blocks of a quantum computer are qubits, quantum gates, and quantum algorithms. You throw three of these in the mix and you have yourself a quantum computer. There are many kinds of quantum computers available these days based on different technologies like trapped ion, Josephson superconducting circuits, quantum dots, photon-based quantum computers. Not only these, but these quantum computers are available, if not all, but some of these quantum computers are accessible to the general public online these days through cloud, for example, the IBM Quantum Experience and others. Rather than just writing essays and thinking about future technologies, we get a chance to participate in the most promising technology of the next 2 decades. And I think it is really amazing. I hope that by now you have covered some of the quantum algorithms. Um, would somebody like to name a few algorithms that you may have studied in the last week? Please feel free to drop your answers in the chat. Okay, since I see no answer in the chat, I would just skip ahead and assume that you are all well versed with basics of quantum computing and some of the quantum algorithms which I saw in the schedule the other day. So now we'll take a leap and jump to learning quantum algorithms itself. I would like to begin with a very simple discussion. Can anyone in the audience solve this linear set of equations? I'll give 30 seconds to anyone who would like to give it a try. It's pretty simple, it's very basic, it's just a simultaneous set of linear equations with two variables. And if anyone just tries it, we know that we can solve it. And the answer is perhaps x is equal to 6 and y is equal to 18. I'm not very good with math, but let's just say it's easy to find an answer for this. But what if I give you three equations with three variables, and so on? Maybe somebody is able to solve a set of three equations with three variables by some method such as Gauss elimination method or something else, or maybe a matrix inversion method. But what about if I give you four equations with four variables? If I give you n equations with n variables, as you can see the pattern, the complexity of this problem scales polynomially with n. In contrast to what you may have been hearing about problems that grow exponentially with system size, this one scales polynomially. But if this problem scales polynomially, then why do I need a quantum computer for such a simple problem? Linear equations in general play a very important role in virtually all fields of science and engineering. They have applications in fluid dynamics, game designing, artificial intelligence, machine learning, chemistry, electrical circuit designs, linear programming, and sometimes very difficult math homework as well. In general, the key idea is solving linear equations is useful to us. Like I already said, for a classical computer to approximate, even just approximate, not solve exactly, the solution of n linear equations in n unknowns scales polynomially with n. And for a very big system of, say, n is equal to 1,000 or maybe 10,000, it takes terabytes and petabytes of data to be able to solve this problem on a classical computer. In 2009, the HHL algorithm was developed and it showed an exponential speed up over its classical counterparts, which were the general methods used by quantum computers, such as Gauss elimination method. And since then, it has been explored in this context to solve linear problems, and it has significant implications in quantum machine learning algorithms as well. The key takeaway is that there exists a quantum algorithm which gives exponential speed up over its classical counterpart as it should. Now we'll talk about the HHL algorithm. It is named after the scientists who developed it, Harrow, Hasidim, and Lloyd. The HHL algorithm approximates a function of the solution vector of a linear system of equations. It also approximates the solution, does not give the exact solution, but the approximation is really good. And its running time complexity scales with log of n, thus an exponentially speed up. The problem statement for a linear set of equations can be phrased as follows, where A is, I think I should turn on a pointer first. I'm sorry about that. Okay. The problem can be rephrased as this. Here, A is a matrix which is a n cross n matrix which can take complex values. X is a vector which we need of variables which we need to find, and B is a vector of coefficients for the equations. For example, A is a matrix like this, X is a variable vector, B is a vector like this. This problem can be written as follows. A simple set of linear equations again. I hope this point is clear to everyone, that how we represent a system of linear equations in terms of matrices and vectors, because this will be used later on. Now we define the goal. We know we need to solve a system of linear equations, but we would shift from the goal a little to be able to understand the working of the algorithm. We would be interested in result of scalar measurement on the solution vector x, instead of the solution vector itself. For practical purpose, we can shift our goal towards finding functions of the solution vector rather than the solution vector itself. We can look at the result of some operator m on the solution vector x, such as its expectation value or something like that. We work with matrices A which are Hermitian for now, so that we can represent A as a unitary operator. In general, this algorithm can work for matrices which are not Hermitian as well, but for now, this would not be the goal. Those implementations are a little bit different than what we are going to learn here today. Now we restate the problem in quantum terms first. First, we map the vectors x and b to quantum states. You can know that a quantum state is generally a Keck vector. So, the problem, the b vector and the x vector, which we assume to be normalized, can be mapped to respective quantum states x and b. Usually, the mapping is used such that the ith component of the b vector corresponds to the amplitude of the ith basis state of the quantum state b. From now, we can focus on this problem. Further, the matrix A is a Hermitian matrix and has a spectral decomposition which is given as follows. Here, lambda j is the jth eigenvalue, and this is the outer product of the jth eigenvector corresponding to the eigenvalue lambda j. Since A is a Hermitian matrix, you should recall it that all these values are real. Similarly, the inverse of the matrix A can also be written in the following form. The basis formed, since A is both invertible and Hermitian, it forms an orthogonal basis. By using basis transformation, we write B in eigenbasis of A, which will be written as follows. Here Bj can be the complex coefficients. Using the rewritten definition of B from the previous slide and A inverse, we can write X as A inverse of B, which will take the following form. The encoding that we have used here to represent our problem is known as the amplitude encoding. It is not very important to know the details of it right now, but I think it's important to know the kind of encoding that we are using. So far, we have done nothing but used linear algebra transformations to map our problem in quantum terms. Next, we begin with the description of the HHL algorithm. The HHL algorithm can be understood within 5 steps. First is state preparation. Second, quantum phase estimation. Third is eigenvalue inversion. Next, we apply inverse quantum phase estimation. And the last step is measurement. The very last step, which is not very necessary within the description that we use, would be the calculation of some observable. Diagrammatically, it can be seen as follows. This is step 1, where we prepare the state, and then we apply a block of quantum phase estimation, eigenvalue inversion, inverse quantum phase estimation, and then we do the measurement. Let's begin with step 1, which is loading data and state preparation. We begin with 3 quantum registers, all set to ket 0. Here I would like to remind you that a quantum register can contain multiple qubits. One register, which we denote by n subscript L, stores the binary representations of eigenvalues of matrix A. The second register, NB, it will contain the vector solution B such that n is equal to 2 raised to power nb. Here n is the number of variables in our linear set of equations or the number of equations that we have. The last register consists of ancilla qubits. First, we load the state B. To go from ket 0 to the state B, the state is prepared by rotating the qubits in register NB to have amplitudes corresponding to coefficients of B. By this, the initial state is just a tensor product of different qubits all set to 0. But now we have the vector B, which has amplitudes of, say, beta 0, beta 1, and so on. And to represent it in this form as ket of B, we apply some rotations and prepare the state. That concludes our step 1. The next step is quantum phase estimation. And quantum phase estimation, in fact, itself is a protocol um, which it is an eigenvalue estimation algorithm. You might have learned about VQE, variational quantum eigensolver, or some other algorithms that estimate the eigenvalue of a system. Like that, quantum phase estimation essentially does that as well. Details of quantum phase estimation would not be appropriate to discuss here today. Rather than how quantum phase estimation is implemented, I would like you to focus on what it does. When we apply quantum phase estimation, it encodes, firstly estimates, and then it encodes the value of the matrix A, which contained the details of the coefficients of our linear equations as follows. The resulting state of the register after we have encoded and estimated the values of the eigenvalues of the matrix A, the resulting state looks something like this. That is the eigenvectors that we saw in the previous slide and the eigenvalues from the matrix A. Basically, quantum phase estimation is used to estimate and encode approximate eigenvalues of A. Next step is the eigenvalue inversion. What we do is we condition rotation of the ancilla qubit based on the encoded eigenvalues. The ancilla qubit or the auxiliary qubit is not part of the system, but it is something we use just to condition the eigenvalues. We impose a condition like this. Here C is some constant which assumes a value less than the minimum eigenvalue. The purpose of performing rotations based on this condition is to amplify the amplitude of the state that we are in, the state of the solution that we are interested to get in. If we apply this block multiple times, we repeat it multiple times, we get the solution, we get very close to the solution state. For that purpose, we use a condition such as the following, where we try to maximize the value of C such as it is minimum than the lowest eigenvalue, but it maximizes the amplitude associated with the state 1. Then we apply inverse quantum phase estimation to go from Fourier basis to computational basis and unentangle the B register from the system so that when we can measure, we are able to measure in computational basis. After we apply inverse quantum phase estimation, you can see that the eigenvalues do not interfere with the system anymore. We get what we need, and that's it. The last step is measurement. When the ancilla qubit is measured, the ancilla qubit wave function, we measure the ancilla qubit. The ancilla qubit wave function will collapse to either ket 0 or ket 1. If it is 0, the result will be discarded and the computation will be repeated until the measurement is 1. The state corresponding to outcome 1 is something like this. We skip the mathematics of it, but it can be seen that it corresponds to such amplitudes. And if you look at it closely, it assumes a form of what we saw in the first slide corresponds to the ket vector x. Here we have inverse eigenvalues, and the eigenvectors of A. Lastly, we can measure an observable, which is a secondary step and not important here. But in short, we were able to approximate the ket x to get a solution of the system of linear equations. To summarize the steps that we did, first we loaded the state B, then we applied quantum phase estimation to approximate and encode the eigenvalues of the matrix A in the phases of the system, and then we applied ancillar rotation conditioned on some constant C to amplify the amplitudes closer to the solution. Then we applied inverse quantum phase estimation to go back to computational basis, and then we measured the ancilla qubit to process the results that correspond to ket1. And later on, we can perform measurement of our observable. The key takeaway is that HHL solves the linear system of equations. Next, I would like to work out an example with you. But before we work out an example, I would like to pause here for a bit to see if anyone has any questions, and then we will move ahead. Okay, if there are not any questions, we can move ahead. Before we go on to solving an example, we can take a break here and look at applications of the HHL algorithm. The most important applications of the HHL algorithm are in machine learning. The classical algorithms are generally limited by a polynomial dependence of the volume of data and dimensions of space. The HHL used in optimized linear or it can be used in optimized linear or nonlinear binary classifier or even support vector machines, which are standard tools in machine learning. Recently, a quantum algorithm was also developed for Bayesian training of deep neural networks, which was based on the HHL algorithm. It is important because it offers us exponential speedups in linear equations, and it is still an active open field of research with many possibilities. Let's now work out an example of the HHL algorithm based on the 5 steps that we learned, which were state preparation, quantum phase estimation, eigenvalue inversion, inverse quantum phase estimation, and measurement. We'll pick our old example, which reads as follows. Again, we begin with 3 quantum registers which are set to 0. As you can see in the previous slide, A is a 2 cross 2 matrix, which will mean it has 2 eigenvalues. So we need 2 qubits to store their binary representations. Therefore, NL is equal to 2. The second register, NB, which contains the vector solution, you can remember that capital N is 2 raised to power NB. Here, capital N is 2. Therefore, NB is equal to 1. We will use only one ancilla qubit. First, we load the state B. As you can see from here, The B vector or the state B is just ket 0. Therefore, we do not need to apply any extra steps in order to prepare the state. Next, the quantum phase estimation protocol estimates and encodes the eigenvalues of A, of matrix A in phases in the following form. Here lambda j are the eigenvalues and t is the time evolution of the unitary, which we saw earlier. For the sake of clarity, we can calculate the eigenvalues of such a small matrix ourselves, but in principle, it is not needed and it is done by the quantum phase estimation. I have the eigenvalues calculated, which are 2 by 3 and 4 by 3. Rather than the actual eigenvalues itself, we are more interested in their ratios. So for the approximation, which is this, which we can get for a value of t equal to 2 pi 3 by 8, it is somewhere around 1 by 4 and 1 by 2. If you can see, the ratio of the eigenvalues in this approximate eigenvalues for the following time value is maintained. This further can be represented in the states as follows. And the corresponding eigenvectors can be easily calculated as to be these. To be clear, once again, this calculation is not needed, and this is what the quantum phase estimation protocol does for us, but we are doing it over here ourselves in order to learn what is happening. Then starting from B, first we represent B in terms of eigenvectors of A. Then we applied quantum phase estimation, which results in the following state of the system. Then we perform control rotation with value of the constant C as 1 by 8. As you can see, 1 by 8 is smaller than the smallest eigenvalue here. When we do that, it leads to a very difficult and a very lengthy math, which the quantum computer algorithm will do for us, but it reads something like this. After that, after the controlled rotation, we apply the inverse quantum phase estimation and we get this. Now we will measure the auxiliary qubit, which is our ancilla qubit, and we look at the state which corresponds to only the ket 1, because that is the state we are interested in. It reads something like this. And if you look at it carefully, it will correspond to our solution vector. Here, this is the norm of the solution vector. Basically, this was it for the HHL algorithm. Its Qiskit implementation, I can share the link later on. It is in the notebook form on the tutorial, and it can be easily worked out. It follows the same steps that I have discussed so far. I would like to stop now if anyone has a question regarding the HHL algorithm before we move on to the next thing. Okay, I see no questions. So I'll go ahead. Some of the ideas that you can explore to work with the HHL algorithm are: you can try to solve a partial differential equation on a quantum computer using the HHL algorithm. You can try to build your own machine learning classifier, and you can see if there's an advantage in using the HHL algorithm. Another question that you can explore is there anything other than the quantum phase estimation within the HHL algorithm you can use to make your own algorithm? If you remember that the only purpose of quantum phase estimation within the HHL was to estimate and encode the eigenvalues of the matrix A. I'm certain that you must remember from your previous learnings that there are more algorithms that can do the same. There might be other ideas that you can explore with the HHL algorithm, and I would be happy to discuss them if should any one of you have any questions or any ideas to discuss. Next, we move on to the variational quantum linear solver. Like it says in the name, it is a variational algorithm, it's a quantum algorithm, and it solves linear equations. It also attempts to solve the linear equations more efficiently than the classical computational algorithms. The VQLS algorithm can be divided into 3 steps. I would not spend a lot of time on this algorithm as it's a variational algorithm, and the basis of it is similar to what you do with the variational quantum eigensolver, which I'm certain that you have learned already. The first step is state preparation. The second is choosing a variational ansatz, and the third is the general classical optimization. This diagram can be seen to understand the basic. First, we begin with the matrix coefficient matrix A and decompose it in linear combination of unitaries with complex coefficients as follows. Here, these are the complex coefficients and these are the unitaries. Then we choose a unitary U which can prepare the state B from the initialized state 0. Then we will begin with an ansatz for a wave function which is parametrized on alpha and which we would like to be our solution. For some parameters k, when the wave function is very close to our solution state, we have an optimal solution. To obtain an optimal solution, we indeed have to construct a quantum cost function which can be evaluated with a low-depth parameterized quantum circuit, then give output to the classical optimizer. This allows us to search the whole parameter space of parameter alpha, and here psi k would be the optimal parameters that we get. So essentially, like we said, we can start off with an ansatz and apply a variational routine in order to get the solution. The cost function that we can employ can look something like this. Here, HP is the projection operator, which can, if you read this, the cost function tells you that how much the wave function that we have, the optimal wave function, is different from the solution wave function that we need. This cost function can be further normalized and to improve the accuracy. And this is not the only cost function that we can employ. In principle, we can construct different cost functions, like we can have different variational ansatz, variational parameters, so on. The discrete implementation of the VQLS is also given. I can share the link with you later on. Now we come to the difference between the HHL algorithm and the VQLS. In principle, they are both identical since they solve the system of linear equations. There is nothing different in that. But compared to the variational quantum linear solver, HHL provides a much more favorable computational speedup. If you remember, HHL gave what we know as an exponential speedup, whereas variational quantum linear solver does not provide with an exponential speedup. But in contrast to HHL, the variational nature of VQLS allows for it to be performed on the current near-term computers, whereas HHL requires more robust quantum hardware and many more qubits. Some ideas that you can explore on the lines of the variational quantum linear solver are up to what limit of our variables n can HHL outperform VQLS. This is something which you can implement the most basic versions of both HHL and VQLS and test out yourself. The other thing you can explore in terms of the variational quantum linear solver would be, can any error mitigation techniques be applied to improve the performance of the variational quantum linear solver? The error mitigation techniques are a bit different from what we know as the error correcting codes. They are in principle very different from each other, and these days error mitigation is a very active field in terms of variational quantum algorithms, not only in context of variational quantum linear solver, but it can be applied to any variational quantum algorithms for VQE, chemistry simulations, literally any variational quantum algorithm. All the concepts that I have covered, you can learn more about these from the Qiskit textbook, which I'm sure you have heard about before as well. With that, I would like to thank you all, and if there are questions, let's talk about them.
Participants, if you have any doubts, please free to ask. Mm. Okay, I think we are arrived to the end of the session. So I once again extend my gratitude to Ms. Sabyatha Gupta for joining hands with us, and I would also like to thank Dr. Manjula Gandhilan for leading and supporting us throughout the process. I thank each and every one of you for joining the sessions. Thank you for your detailed presentation, and it was exceedingly informative.
Thank you, everyone. Bye bye.
Bye.